Now there's a ruler here. I'm trying to balance this ruler at this particular point. This ruler, the total weight of this ruler tends to act from its center. So I'm trying to balance it. So what I'm going to do, I'm going to put some weight on this side, and then let's see what happens. So this is a weight of there's 1, 2, 3, 4, 5, mass of 50 grams. So this is 50 grams. So what I want to do, I want to put it from one side of this ruler. Now, as you can able to see, it may not probably horizontally. The ruler may not be exactly horizontal as you expect when in balance. But then, for now, we can able to say that it is balanced. Now, what I want to do is this. I want to put this weight at this particular point. So I want to put the weight at, let's say, 76 centimeters. I'm still holding on this side, and so you're going to see. Remember, this roller is able to turn about this particular point, so this is our pivot. I have put some masses here at 76 centimeters. Now, there's this ruler here. This ruler to balance at this particular point, as you already mentioned. Now, what happens is this. I have, these are 20 grams each. So 1, 2, 3, 4, 5. So this makes this to be 100 grams. That is 1 Newton. So I want to place this 1 Newton at a particular point, and then we see its effect on the roller. So let me just a little bit so that. So this is the pivot of the ruler. This is where the ruler is able to turn about. This is the pivot. It's able to turn either in a clockwise direction or in anti-clockwise direction. So when I put this mass on this side of the ruler, let me place it at, let's say 65. So 65 is measured from this side. So when I say 65, is exactly at this particular point, or 35 from the other side. So this is, let me use a 65. So for this particular point, if I try, when I'm trying to release the ruler, you can able to see the effect of the weight. This weight, which is 1 Newton force, is acting such that it makes the ruler to turn about the point, to turn about this point here. So if we want to find out by how much is this weight turning the ruler, by how much does it do that at this particular distance? When we ask that kind of question, we are asking about what is the moment due to this force about this point here. And that is what I want us to find out. So once again, I want us just to confirm. So I've placed it at 65 centimeter mark. And I'm just holding it with my hand so that it doesn't fall down. Of course, that is common sense. You can be able to see. So I want us to work out the moment due to this force here. So I have to remove it. Now, the 100 Newton was placed at 65. So place at 65 centimeter mark. That is where we had our weight. That is 1.0 Newton. So we know that, or if you can able to remember, that moment due to the force is given by force times perpendicular distance, and that perpendicular distance must be from the pivot. The distance we're talking about is here. This is the pivot. This is where the roller tends to rotate about. So the force is 1.0 Newton times the distance, which is 65. So 65 minus 48.5. Sorry, it's 48.4. So that is 6. 14 minus, that is 6. And we have borrowed 1 here. So that makes here to be 5. So that is 16. So this is 16.6 centimeter. So we have 1 times 16.6, 1 times 16.6, that will give us 16.6, and then Newton times centimeter, that will give us Newton centimeter. So this is the moment due to the 1 Newton force. But then we need to add its direction. It acts in a clockwise direction. So if you're supposed to ask which type of moment is this, this is a clockwise. The clockwise moment. So the clockwise moment due to the force is what you're getting as 16.6 Newton centimeter. Now, let's say now we put both sides and try to weigh. So I want to balance another force with a known mass. I want us to balance the other side with a known mass and then try to work out the moment due to that force. And then we are going to measure its mass to compare what we get from calculation. I have some mass here. Of course, we know the metal part, its mass, but then I've just added some model clay here, just to give us any other mass, and then we want to use with this. So we have known mass, and when we have the unknown, so we are going to try to apply the principle of moments to prove. So I'm going to place it at, can even place it here at 50. So this one is trying to balance. And then for the, you can place this here, let's say at 72. So we are going to use this to try to balance the other side until is approximately or equal to. So just approximately where they will try to be equal to. That is what we're going to use. You know, this is an experiment, so why do I feel that I'm lucky? Alright. Yeah, I think this one is going to work. This is going to work. Actually, it's not actually rotating clockwise or anti-clockwise. So there's no vertical rotation. There's just horizontal rotation, which we can just try to see to minimize that. See if we can able to minimize the vertical horizontal rotation. But we get it now. This is at 72 centimeter. Approximately the the string is too thick, so there's going to be some part for error or uncertainty. And then this is placed at exactly, so this is exactly at 23. So from this side, this mass here, which is now the unknown, is at 23, The pivot is at 50 centimeter mark, while this is at 72 centimeter mark. So let's now try to calculate. We do calculation, and then we see if we can able to work out, and then we're going to compare with the value that we're going to measure. That is our next part of what I want us to do. As you can able to see, the pivot is at 50.0 centimeter mark. The 1 Newton is at once again, there is a 72 centimeter mark, and then the unknown weight, which I'm going to call F, is at 23, approximately 23.0 centimeter, 23 centimeter. Now the string is a little bit thick, so probably we may not actually get exact answer. It's like almost an approximation, which but then let's try to work it out. Now this roller here is balanced. This force on this side will tend to make the roller to turn in a clockwise direction, this way, in a clockwise direction, if it is the only one that is acting. This weight here will tend to make the roller to move in a anti-clockwise direction. But now that the roller is balanced, it means that the moment on this side, which is the clockwise moment, must be equal to the anti-clockwise moment. That is the principal moment, and we want to find out if indeed that is going to work. So we need to find the distance from here to here. So that is 50 minus 23. Remember, 23 is from 0. So this is just 23 centimeter mark. So from the force F to the 50, that is 27 centimeter. So the anti-clockwise moment must be equal to clockwise moment. The anti-clockwise moment is force F times the distance to the pivot, which is 27 centimeter, and this is equal to the clockwise moment, which is 1.0 newtons, times 72 minus 50, that is 22 centimeter. So that is 22 centimeter. Therefore, from here we can divide both sides by 27 centimeter, divide both sides by 27 centimeter. So 27 cancel this side, of course centimeter cancel that, so we have F times 1, which is F. F is equal to 1 times 22 divided by 27, and that gives me 0.8148 that one newtons. Why newtons? You can able to see clearly, centimeter cancel centimeter, and so we have 0.8148 newtons. Into two significant figures, this will be 0.81 newton. So our work is to see if we measure the weight of this object here, will it be close to this value here? Because that is what the principle of moment is showing us, that that is the value. So we need to find the mass. Let's find the mass of this unknown weight, and that is 87.5 grams. So the calculated from the experiment, we get 0.81 newtons, but then the measured value, we are getting the the mass as 7.5 newtons. So that means the weight is 0.875 newtons. If we compare with this, for us to compare, let's give this value in 3 significant figures. So that is 0.815 newtons. So the difference there, if you minus 0.85, so that is 0.060 newtons. So the difference is very small. So the difference in weight is 0.06 newtons. This difference is very small, so therefore we can conclude, let me just get a percentage difference, that is so the percentage difference is 6%, which is below 10. So our value was very close. The only thing that to get the reliable results, what we can do is to repeat the experiment. Sorry. There's a question here where there are two pivot, or specifically there is no pivot. So you're the one to choose the pivot, or the question can able to give you a hint on where there is a pivot. And the question read, the figure 3.1 shows a boat that has been lifted out of a river. The boat is suspended by 2 ropes. So in this case, there are now 2 ropes, and it is stationary. So it's balanced. So that means the forces acting upward and the forces acting downward, they are equal. So therefore, the resultant force is 0. And then now that is stationary, it doesn't move, it doesn't rotate. So that means clockwise moment also is equal to anti-clockwise moment. So we have the forces there, T1 and T2. And before we work out this question, I want to show you how the setup can be done in experimentally in school. So I have 2 stands here. I have 2 stands, so which are going to support this weight. So in this kind of situation, you can able to see is a little bit different from the other one. There's that we expect to be 1 pivot, but then this ruler can either turn in this direction. If it turn about this particular point, that means we ignore the other side. And then it can also turn about this particular point, depending on the weight. So if you have this, if the tension, this is the tension and is acting on this direction, you can able to see this become our pivot. If you fix this side and then you remove this end here, then this become our pivot. So this is an interesting question, and you're supposed to choose the pivot to use. The weight of this ruler is acting downward. So if you take this side to be the pivot, that means you will have the tension that is acting, of course, upward, but the weight will also act downward. So this weight will also have moment about this point. The tension will also have moment about this point, and you can able to see this distance here. This is the similar situation that is being tested as application from this question here. So let's see how we can able to use this little knowledge here to understand what is happening in this question. Now from the diagram, let me just have this. From the diagram, we have the weight acting. Where the weight is acting, that is called the center of mass or center of gravity of this. And then we have the ropes that are tied, and of course the tension is acting upward. And then there's another support from this side, the tension. So this is a T1, this is a T2, and the weight is acting. So we have been given this distance from here to here. So this distance is 1.2 meters, 1.20 meters, and then the other distance this side from here, that is 0.4 meters. Remember, it's just a sketching, so it's just a drawing. Now the weight is 24 kilonewtons. So the first question we are being asked, determine the moment of the weight of the boat about the point P. That word is very important. About the point P. About point P. When the question tells you something like this, about the point P, it means that take P, which is here, take P as the pivot. Take P as the pivot. So, if you look at that, so we are going to assume that this is going to turn about this particular point. So, if it is the tension that is acting, if it is only the tension that is acting, it will make the boat to move in that direction. And that is a clockwise direction. But if it is the weight that is acting, you can be able to see the boat will be able to turn in anti-clockwise direction. So that is what we are applying here. But now that they are stationary, now that the roller doesn't move up or down, or doesn't rotate about the point P, so it means that what moment due to the weight of the roller that is acting downward is equal to the moment due to the tension that is acting also in this direction. But then, number one, moment due to the weight. Remember, moment is given by force times distance. This distance is the distance, perpendicular distance from the pivot to where the line of action, to where the force is acting. So that is 24 kilonewton times the distance, which is 0.4 meters, and this will give us 9.6, so that is 9.6 kilonewton. 9.6 kilonewton, this is just 9,600 newton. Oh, sorry, remember this is newton times meter, so this is supposed to be newton meter. So this is newton meter as the unit of that. Now, the next question, we are asked to find the tension. We are asked to find the tension T1. So just the way I've demonstrated there, the moment due to T1 should be equal to moment due to the weight. But what about T2? So if we are talking about T2, T2 is here. This is where our pivot is. Moment is supposed to equal to force times distance. But this tension here is acting at the pivot. That means distance is 0. So at this particular point, when you take moment to be here, that means moment due to the tension T2 is 0. Kindly, let's note that. Moment due to T2 acting at the pivot is 0. But mark my words, I did not say that T2 is 0. I said moment due to T2 is 0 because it is acting at the pivot. So now, moment due to T1 is equal to T1 times its distance, that is from where T1 is acting to the pivot. That is 1.2 plus 0.4. So 1.2 plus 0.4, that gives us 1.6 meters. This should be equal to moment due to the weight that is acting in the opposite direction. So that is equal to 9,600 Newton meters. So to find T1, this is equal to 9,600 Newton meter divided by 1.6. And just to confirm, 96 divided by 1.6, that is 60. So that is 6,000 Newton. 6,000 Newton. This is meters. Sometimes if you've forgotten what to do, you can able to see clearly. Meters cancel meters, so our unit remains Newton, just in case you may forget the unit of the tension. Now this is very interesting. Now Roman 3, we have been asked to find T2 now. Find the value T2. So to find T2, we are now going to apply the second condition. Remember this, for us to find this, we have to confirm that clockwise moment is equal to anti-clockwise moment. Now look at this ruler here, which is representing our boat here. Now the boat is stationary. There is no movement by the boat. What does it mean? Apart from clockwise moment equals to anti-clockwise moment, the tension T1 and T2, they are acting upward. The weight of this roller is acting downward. This roller doesn't move either upward, doesn't move downward. What does it tell us? It tells us that the upward forces is equal to the downward forces. Therefore, T1 plus T2 is equal to the weight that is acting downward. So T1 is, we already found it here, that is 6,000 Newton, plus T2, which is equal to W, that is 24 kilonewton, that is 24,000. So therefore T2 is equal to 24,000 minus 6,000, and this gives us 18,000 newtons. And that is how we apply the principles of moment and the resultant force in working out a question that involves two pivots. We're supposed to choose one. Have a nice time and see you next time.